Okay, so this is the parallel summary lecture. And so you see I've drawn a parallel example with E source applied here and our individual branch currents, our R branch, our L branch, and our C branch. We know that these are both reactive currents, so based on the fact they're reactive currents, they're going to be 180 degrees out of phase, and we're going to have a net reactive current. In the series circuit, we had a net reactive voltage. Here, we'll have a net reactive current. The thing to understand here is it's going to be as we know from our previous study, the smallest opposition is going to have the greatest current. So in this case, it'll be the smaller of these two reactances that's going to determine the net value of current. Whereas in the series circuit, it was the larger of the two reactances that determined the net reactive voltage in the triangle. So we need to kind of understand that going in here. Now, because we have a parallel circuit, we know that our reference value here is going to be voltage. We're going to have the same magnitude and phase for voltage all the way across. As you can imagine, there's no way we could have a maximum voltage of a sine wave for the resistor at the same time as we had a minimum voltage for the sine wave for the inductor, but we can so for the currents. So currents can be out of phase, but voltages can't. So here then, if we were to look at this, we would say that we have an E source value equal to a VR value equal to a VL value equal to a VC value. The voltages are all in phase, and we'll use that as our reference for going forward for this analysis. So next thing we're looking at is the total impedance. So when we're looking at the total impedance, remember, we can't just simply add up these values of opposition because that would be treating them as if they're in series. So we can say that Z total equals 1 over R plus 1 over XL plus 1 over XC. 1 over is going to give us the results. That's true. We've got to remember that we've got to take into account the angles or the polar values or rectangular values of this. So this would be 1 over R plus 1 over plus JXL plus 1 over minus JXC, 1 over, and you process that in your calculator and you will get the total opposition or the Z total value. So don't forget that when it comes to parallel, we have to do that. Now, once we've come up with the result here, we'll have the equivalent impedance. That equivalent impedance can be expressed as a polar value of, let's say, R plus J, or I said polar value, a rectangular value is R plus JXL, provided it's primarily XL, or an angle of Z total at an angle of phi or phi for the polar value. But remember, when we do, this is indicating for this parallel circuit what is its equivalent impedance as far as a series connection goes. So there's a process. It doesn't go directly to this based on just plugging in the numbers like we can in series. It's a process of doing your product over sum of your parallel equation to get this result. Okay, so then when we go forward then, because we have a parallel arrangement, we're going to be looking at a current triangle to prove Kirchhoff's current law, right? So when we look at these voltages, we certainly know that one of the currents is going to be right in phase with that voltage. And as you know, that's always the resistive branch, isn't it? Resistive voltage and current are always in phase. Inductors are always 90 degree displaced, capacitors 90 degree displaced. This one's lagging, this one's leading. Okay, so if we're going to put that IR value in here, it's going to be right in phase with the applied voltage, and we would label this IR. IR at 0 degrees. Now, when it comes to the inductor, well, remember, it's our acronym ELI that's going to describe that relationship. And Eli says the current is going to lag the voltage. Where do we find the voltage? Right here. We set it as our reference. That means our current, IL, is going to have to lag that voltage, right? Remember, a lagging current for an inductive branch. So now we've got IL down here. I think you get the idea when it comes to the last branch, the capacitor branch. ICE is going to describe that relationship. Where do we find voltage? It's right here as our reference, as our applied voltage equaling VC. We know the current in the capacitor branch has to lead the voltage, and so we're going to have IC indicated here. Now you know, with this being a plus J value and this being a minus J value, that when we add the two together, and we know we're always adding currents in Kirchhoff's current law, if we're adding these two together, if the minus J is greater than the plus J, you're going to have a primarily minus J component. If the plus J is greater than the minus J, you're going to have primarily a plus J component. Let's assume that we had a primarily capacitive current. That would be as a result of XC being less than XL. You have a primarily capacitive current. That means your total current is going to be right here, right? So I total will be found right here. If we look at making sure that's consistent with our ICE relationship, right? That's where ICE should be consistent here. That means we'd have current leading our voltage. Where do we find voltage? Right here. Where do we find current? Right there. Here's our circuit phase angle, angle theta. What do we notice? We notice the current is leading the applied voltage, as it would be for a primarily capacitive circuit, where IC is greater than IL. If we look at the opposite condition, where we have IL greater than IC, that means our minus J component is going to be greater than our plus J component. That means our XL value is less than our XC value, giving us the greater current of the two. And we end up with a theta that's represented here. If we've chosen the reference as the applied voltage, this is a lagging current. And we know that Eli should be indicating that relationship if we've done this all correctly. And this is our verification that we've drawn this all correctly. We can see that primarily IL is going to have to be Eli, and we have a lagging current from our voltage. Okay? So that's going to give us our I total value. And that can simply be done by rectangular to polar conversion, or vice versa. Once we have this value of IR and this value of net IL, that becomes a rectangular representation of I total. You can do a polar conversion in order to get this angle and that magnitude, right? You don't need to use Pythagoreans and all that. You can just use your calculator for those conversions. Okay? So this is the parallel example, and what I would just do is bring up something to consider here for a moment, and it's something that maybe initially is maybe a surprise to you until you really think about it. So my question would be, is it possible for any reactive currents in this circuit to be greater than the total current? Based on what you know, you would say there's no way that you could have a branch current greater than the total current in a circuit. How is that possible? What we have to realize here is when we're looking at this, it clearly is possible. What if you had an IL value equal to an IC value? So let's just suppose we had IL equal to IC. Let's say that IL was equal to 450 volts. 450, I should change that, sorry. Make that 450, or 45 amps. IC is 45 amps. We're working with current here, sorry. So you've got two currents of 45 amps and IR, let's say, is only 10 amps. If this is 45 amps and this is 45 amps, the net reactive current is 0, isn't it? So 45 amps, 45 amps. The net reactive current is 0. The total current then is only going to be made up of a 10 amp resistive branch. So if we had 10 amps here, 45 amps here, 45 amps here, that is a value of total current that would be read here as 10 amps. Yet, we'd have two branches that, when read individually, would be 45 amps. So an ammeter here would read 45 amps. An ammeter here would read 45 amps. An ammeter here would read 0. Because you've got to remember, these two currents are 180 degrees out of phase. So as a result, their total current is IL added on to IC plus J45 added on to minus J45 gives you a 0 net value. That 0 net value, when added to this 10 amps, is going to give you 10 amps, and you're going to have an I total value. You're going to have an I total value of 10 amps. But this is, this is indicating that you can have branch currents greater than the total current in parallel. So then you'd have to conclude for series, you could have drop voltages greater than the applied voltage. So don't forget that. So don't be confused when you're doing maybe some exercises and you've got 120 volts applied and you've got over 300 volts for a reactive component. As long as there's RLC, that is to say there's inductance and capacitance in a circuit, that can happen. You can have series voltages greater than the applied voltage. You can have parallel currents greater than the total current. Okay, so that includes that summary.